very much for having me here. My name is Eli Ben-Sasson. I've been doing research on I've been doing research on technologies related to scalability and privacy for the past almost 20 years. And I'm here as a co-founder and chief scientist of StarkWare. So a little bit about StarkWare. We are an Israeli startup. We have around 30 team members. By the way, we are hiring, both engineering and product. We've raised over $40 million, combined of 2 rounds of equities, a seed and an A, and we received a sizable grant from the Ethereum Foundation. The 2 main things that we are currently working on, the first and most important one is our product, which is a scalability engine for exchanges over Ethereum. We have demonstrated the alpha version of this product in June. This was joint work with the 0x project. And I'll say a little bit about this later on. And we hope to be live on mainnet serving real exchanges. The CEO of Coinbase has already announced that they are working with us, and we have others that we are talking to. We hope to be live on mainnet by the first quarter of 2020. Hopefully, maybe even early there. And another project that we are working on is a Stark-friendly hash function. We are hoping to reach a selection that we can offer to the Ethereum Foundation. This is the purpose of the grant that we received from them. And it is funded by the Ethereum Foundation. Our delivery should be by summer of 2020, less than 1 year from now. And if you want to hear more about Starks and StarkWare, you are welcome to join us at StarkWare sessions that will be running here in Tel Aviv tomorrow. So please reach us if you're interested. Okay, I want to give a little bit of context about Starks and where we can interact with blockchains. So in the past, financial systems worked in the trusted party model that also required delegated accountability. For most of human history, financial systems had an underlying implicit trust in a central authority. This was the king, the state, a central bank. And if we wanted to know that the system has integrity and that it operates accountably, then the process of accountability was delegated to human experts, auditors, accountants, regulators that were delegated by society or by government to come and inspect and report that everything is okay, that the banks, the financial systems are operating with the integrity we expect them to operate with. Now, this is all in the past. The future that was ushered in by Bitcoin and other cryptocurrencies, Ethereum and others, talks about a different model. In this model, it is decentralized, permissionless, and blockchains thereby remove the trusted party and create a trustless and inclusive alternative to accountability, which means that the process of accounting for the integrity of the system is not delegated to a particular cabal of experts. It is rather an inclusive process. Anyone with a laptop should connect to the internet and be part of this process of verifying the integrity of the system. So this is a beautiful idea that resonates very well with concepts of democracy, human dignity, inclusion, and things like that. But it also has 2 fundamental problems that we are all acutely aware of. The first one is that of scalability, and the second one is privacy, because in the model that we have right now, there is no real division of computational labor. Each node that is on the system is invited, but also required, to verify all aspects of the system, all the transactions. And this means that in order to scale up, you would seemingly require all participants to scale up their computation and bandwidth, which is not a desirable thing. And at the same time, the problem of privacy is that if everyone checks every aspect of the system, then everyone also inspects and sees every aspect of the system. And thereby you lose or compromise privacy. So these are 2 well-known problems. And just to illustrate, so Alipay that you see on the left has a TPS, transaction rate per second, of 100,000 or more, whereas Bitcoin and Ethereum and similar decentralized cryptocurrencies are sort of stuck right now at a limit of 7 or 10 transactions per second. And this is technology that started just 10 years ago, so you would expect it to scale much better. But the ideal of inclusive accountability is this property that sort of puts the limit right now on scalability. So this is the problem, and we think that there's a good solution that is encaptured in this family of technologies, of these proof systems that are ZK Starks. So I'll say a little bit more about what kind of proof systems constitute a ZK Stark. ZK stands for zero knowledge, and it is a property of proof systems that provides privacy. You can think of it as shielding away some of the inputs and hiding them without relinquishing the ability to verify integrity and correctness. So it's a magical property that was, discovered 30 or more years ago in the mid-'80s, and has been a very dominant theme in theoretical cryptography and more recently in deployed systems today. So zero knowledge can help solve the privacy. Now the S in the word Stark stands for scalability, or you can think of it, one aspect of it is having succinct proofs that compress the computation and that are exponentially smaller than the amount of computation that is asserted by such a proof. So systems that have succinct proofs, that have zero knowledge, offer the ability to solve the two problems of privacy and scalability of blockchains. And this is what StarkWare is attempting to do. So a little bit more about a Stark system. The scalability of a Stark system comes from the fact that the proof for a given amount of computation is exponentially smaller than the amount of that computation. So as you scale up the computation, the proof size scales up exponentially smaller or only logarithmically with the size of the computation. At the same time, it's not just that the communication complexity, the amount of the number of bytes that are sent is smaller, also the processing time associated with verifying such a proof grows exponentially smaller than the naive computation time. At the same time, generating such proofs is nearly linear. In mathematical terms, it's quasi-linear, so it's very close to linear proving time, or it's almost the same time required to do the computation as it is to generate the proof. And finally, there's this aspect of universality that means that you can apply such proof systems to any computation, not just the very specific ones. The T in the word Stark stands for transparent, which means there is no trusted setup. All aspects that come from the public verification process are just random coins that can be sampled by anyone or by a blockchain. And this transparency in particular implies there's no toxic waste or no setup ceremonies required. And another bonus of some Stark systems, the one that we're deploying, is that they are plausibly post-quantum secure and rely on very lean cryptographic assumptions, which makes them a little bit more amenable or trustworthy on an ongoing basis. So I want to explain a little bit in more, graphically what it means to have scalability through Stark systems. So suppose you have something like, the amount of transactions that you would like to scale up. So what it means is that you would like to follow this blue line. And if you do this on Bitcoin today or on Ethereum, as you increase the amount of transactions per unit of time, let's say per block, you would require everyone to naively replay and check all of these aspects and verify them time and again. And the amount of computation each node would have to carry out would be similar to that of the whole of the amount of transactions. It would grow linearly in it, and that's this sort of dark blue line. So a proof system like a Stark comes in and does the following thing. There's going to be one prover, that's the sort of orange-yellow guy up there, that will process the transactions in time that is slightly more than linear. So it will work harder than it would be necessary for everyone to verify those things. But for the price of that, the verifier complexity goes down exponentially to something that looks like the logarithm of the number of transactions, which means that it scales very slowly. And what everyone needs to run is just the verifier. So how does this interact with blockchains? We have at our disposal vast amounts of computation, say on the cloud or on big servers, but we're not expecting everyone who wants to do inclusive accountability to have access to these big resources. So off-chain we have this vast amount of computation, and this is what the prover is going to tap into. But on the blockchain, we have very limited computation because we want to maintain inclusive accountability. So we have this block limit that is very severe. Well, all we need for inclusive accountability is to verify proofs, and verification is exponentially smaller and more efficient than the amount of payload. So what we have is this scalability factor. It is the factor between the amount of naive computation that is attested to and the amount of time needed to verify it. And that's exactly how you get scalability, by using ZK Starks. Okay, so I guess you don't care so much about our own stand-up, so let's cancel that. Okay, I want to compare Starks to some other prevalent technologies that are out there in the blockchain ecosystem. So perhaps the most famous by now are the ZK Snarks used in Zcash, which I happen to be a founding scientist of. So they're wonderful in helping with privacy, but for scalability, they are subpar. First thing is that they have a trusted setup, which is the dark red line there. And this trusted setup phase grows linearly, or more than linearly, with the amount of computation. And when you look at prover complexity and verifier complexity in terms of running time, they don't scale as well as our ZK Starks do. Another version of this is the use of recursive snarks, which shortens by a large factor the amount of trusted setup. It becomes very short. But in exchange for that, both the proving time and the verifying time grow up to be much, much larger and costly, which means that as a scalability solution, they're not so great. The last one that is used out there, and by the way, recursive snarks are going to be deployed by O of One on the Coda cryptocurrency. The last one that is out there is bulletproofs, that is already used by Monera. It's a zero-knowledge technology. It's very good for privacy, but you will notice, and it is transparent, it doesn't require a trusted setup, but you will notice that the verifier time actually scales super linearly with the amount of computation. The size of the proof or the communication grows logarithmically, but the verification time grows super linearly, which again means that it's not a very good scalability solutions. So to summarize this, there are other technologies out there, and as we're talking, there are more and more coming out every day, but we still think that our ZK Starks have some advantages that are really good, both for scalability and also for privacy. And again, tomorrow we'll have a full day discussing both the science and the applications of our technology, so I invite you to sign up and attend that. So a little bit about our product. As I said, we have a live system, StarkDex. So the alpha version of it has gone live in June. And what we did is we used the scalability of Starks to scale up the amount of trades that can be settled on the Ethereum network. So each batch in this alpha system was 1,024 transactions. The proof itself fit inside a single Ethereum block. And this is a live system. You can actually go and check the verifier contract code and the main contract code. And if you type StarkDex.io, you can go and see the system operating. Now, a little bit about the stats of this thing. It was 6,000 gas per trade, compared with 100 to 200,000 gas for settling a trade without our system on Ethereum. When we were running it, it takes only 15% of Ethereum's network capacity. We ran it at a sustained rate of 10 TPS. We used a live sampling from Binance feed, so some real trading that we simulated. We settled over 10 million trades over 2 weeks with an average latency of roughly 10 minutes, and it takes 6 million gas, which is below the gas limit of a block of Ethereum, to verify a batch of 1,024 trades. Now again, since then we've progressed significantly, including with these numbers, and we'll talk more about this tomorrow at StarkWare sessions. So the functionality that we supported on the alpha was depositing to the system, withdrawing from the system, settling only maker-taker orders, and we dealt with multiple assets. Again, this was 4 months ago. By now we've improved it significantly. I don't want to steal the lightning of our speakers tomorrow, but if you're curious to hear where we're at now, please come tomorrow. So this is what scalability looks like when you look at amortized gas cost, the effect of it on Ethereum. So as you increase the batch size and you look at amortized gas cost, it goes down significantly. So for a batch of 1,000 trades, that's this point, you pay a cost of just a little below 6,000 gas per trade. We already demonstrated a few months ago batches of 8,000 transactions per block of Ethereum, which goes below 1,000 gas per trade. And again, if you want to hear more at where we're standing at today with some surprises, please join us tomorrow. Thank you very much.